Last time I think we ended the discussion talking about Griffith's demonstration that on average, identical fermions tend to spend more time farther apart, or in other words, when we measure their positions, we tend to measure them at positions that are farther apart, regardless of the states that we use to anti-symmetrize them. So I imagine here that we're taking a state where particle 1 has a Gaussian distribution as a function of x, particle 2 has a Gaussian distribution as a function of x. Nothing particularly special. One's centered at x equals 2, one's centered at x equals -2, and when we anti-symmetrize and symmetrize, we get these wave functions, and the corresponding level curves are shown over here. And what you can kind of see is that, the probability of finding the identical fermions close to each other is reduced. Here's where they're at the same location along the middle, and their peaks tend to be well separated right there. My pointer's having trouble here on my laptop. Whereas the bosons, when we symmetrize, tend to be closer together because it doesn't go down so far in the middle when we square that and get the probability density. And I wanted to this is a little bit confusing when you look at the probability density as a function of x1 and x2. Again, sometimes people think, oh, are there two different x-axes? No, there's just one x-axis, and both particles live on that x-axis. And perhaps there's a different way of displaying things, and that's what I want to kind of get at here. Of course, in the distinguishable case, where we know the difference between these two particles, there really is information in this full probability density. Whoa, I'm really having trouble with this thing. So there, where exactly little lumps are in there is all new information up there. Whereas there's some kind of redundant information in this, right? We could tell that because it's got to be anti-symmetric with respect to the line x1 equals x2. And this one's got to be symmetric with respect to the line x1 equals x2. So we don't really need the entire probability density. There's some redundant information in there. So instead of displaying things as a function of x1 and x2, where we're going to seeing what the probability density is in a region of measuring particle 1 in some region and particle 2 in some region, I instead want to ask the question, if we just measure a particle's position on the x-axis, what's the probability for finding a particle? And I don't care which. And we're going to compare that probability density for the distinguishable, identical fermion and identical boson cases. So let's think about how we might do that. Suppose I said this, it's not very carefully labeled on here, but this is the x2 axis going up there. This is the x1 axis going along here. And suppose I say, I don't really care where x2 is. I just want to get the probability density for particle 1. How could I take the full probability density as a function of x1 and x2? Let's take the distinguishable case first, and just reduce it down to saying, hey, I'm not even going to measure where x2 is, where particle 2 is. I'm just going to measure particle 1. Maybe it's a proton, and particle 2 is an electron. I'm just going to measure the position of a proton. How can I get that probability density for just particle 1? If I know exactly what this function is, or let's say the magnitude squared of it, I've got the probability density. What would I do to that probability density to display it just as a function of, or just to tell me what's the probability density for measurement of particle 1 only as a function of x? I don't care where particle 2 is. I'm not even going to look for it. I'm not going to measure it. Yeah, we would just say, I don't really care what's going on along this direction. I might bin this up and say in the vicinity, I'm really having trouble with my pointer today, but in the vicinity of 2, integrate all this probability density and get a sort of integrated probability density in the vicinity of 2 and in the vicinity of 3 and so on. So I'm just going to take this function of 2 variables. Well, first I'll take the magnitude squared of this and integrate with respect to x2, and that would give me the probability density as a function of x1 for measuring particle 1 as a function of x1. And that's going to be different in general than the probability density for measuring particle 2 in this case, because they're distinguishable. You know, this particle 2 is more likely to be found near -2. Particle 1 is more likely to be found near +2 in this cooked up example I have here. So if I wanted to do the other one, of course, I would just integrate across horizontally to get that probability density. And then if I wanted to say, well, I don't really care which particle I find. I don't care if it's particle 1 or particle 2. I've got those 2 probability densities. How could I put them into an overall probability density that say, hey, if I measure a particle, I don't care which particle, either one, what's the probability as a function of x for finding that one particle, whether it be the electron or the proton, as a function of x? Well, we could just add those 2 probability densities as a function of x and then multiply each one by 1/2, right? Because otherwise our total integrated probability would be 2 under the curve. So we're going to weight them equally. So that's what I'm going to do for that. That's the most complicated case, thankfully. That's what I'm going to do for the distinguishable case. And that will answer the question, what is the probability as a function of x for finding any particle as a function of x? I'm really struggling on my laptop with this pointer. And unfortunately, I've got so many things plugged into my laptop, I don't have any more. Yeah, there's no good way for me to point with this. Well, maybe what I'll do is take this out, put this in. Sorry about this. And if I plug in the wrong thing. All right, that didn't work. I really want to be able to point for the purposes of people on Zoom, but it's not working so well. Let's try this again. There we go. Okay, we'll see if that holds up. The idea is there's some redundant information here. If you look at the identical fermion or boson case, it doesn't matter whether I integrate along x2 to get a probability as a function of x1, or I integrate along x1 to get a probability as a function of x2. So in that case, I don't have to kind of multiply, add the 2 together and multiply by 1/2. I just do it once, integrate along x1 and get the probability as a function of x2. And that would answer the question for identical fermions, 2 identical fermions on the x-axis in a certain state, each one, the total 2 particle state being something particular. What is the probability as a function of x of finding one of those particles as a function of position? And so what I'm going to show you is now what that looks like. So what I'm going to do is imagine that I put these 2 particles in a situation very similar to what I've got here. I imagine one of the particles is located at x equals -2. And I'm going to make it have a Gaussian distribution. So it's in a Gaussian state around x equals -2. The other one, a Gaussian state centered at x equals +2. And we want to display that probability for finding a particle, either particle, as a function of x. And then I'm going to let the particles get closer and closer together, and we'll see what happens. So let's go to MATLAB here. Okay, so on the left figure, everything looks pretty much the same. So on each figure, the dashed and the dotted black curves just represent the individual states of the two particles. One right now is a Gaussian centered close to 5, maybe at x equals 4, and the other one at -4 or something like that. That's what the dashed and dotted curves look like. And then the blue curve is the probability density as a function of x gotten the way I just showed. So it's the probability density as a function of x for if I measure the position of a particle, and I don't care which one is which. I have no way of knowing which one is which for bosons or fermions. What's the probability density? In this case, there's hardly any overlap. And notice it agrees with what we said before, that the probability density doesn't really make a difference whether they're distinguishable particles or identical bosons, which is on the left, or identical fermions, which is on the right. But as those two Gaussians come closer together, so I'm going to show what happens as we move them closer and closer together and actually pass through each other. What does that probability density look like as a function of x? So I'm just slowly moving them together. Still not too much difference, although you may notice that for the bosons, the center is getting a little bit higher there of the probability density. They're more likely to be found near each other, whereas for the fermions, it's starting to dip down a little bit in the center compared to the distinguishable case in the middle. Notice the Gaussians are now starting to overlap substantially, and the bosons, when we symmetrize it, tend to have more probability of being found together. Okay, and the peaks of the individual Gaussians, notice, are starting to get close to each other. I want you to, in particular, pay attention to what's going on to this fermion distribution as these two peaks, which are moving towards each other. I'm just sort of artificially moving the two particles toward each other, but they're fermions, so we got to anti-symmetrize. I want to make those two Gaussians pass through each other. Look at what happens to the shape of that blue curve on the right as they pass through each other. The other two, of course, get very peaked in the middle. They're essentially right on top of each other. And notice that, I mean, one not so interesting thing is that the distinguishable and the boson probability densities are exactly the same in that case. And that's because if you symmetrize the distinguishable case, of course, there's nothing, it's already symmetrized if they're the same state. So there's no difference between distinguishable and boson if the two states are the same. Not so for the fermion. If you watch those two come together, you notice that the two peaks, we sort of had a double peak, and the peaks sort of moved closer together, and then they came in and they paused and they kept that separation. Even though they're overlapping now, these individual side peaks are still quite far apart. And they keep that separation, even as they pass right through each other. And then when they start to get far enough away from each other, then the peaks move farther apart. So that's kind of an interesting feature of fermions, that even though I'm sort of indicating that these particles are almost right on top of each other, they have two separate peaks that stay far apart. And we can't really see that process of them passing through each other in terms of that combined probability density. Here's another way to look at the same thing. Let's see, if I just go like this, I'll end this as soon as I get to the end here. All right. Let me show now a bunch of identical fermions. We haven't talked about more than two, but the process of anti-symmetrizing for a whole bunch of identical fermions. Here I'm just going to be displaying fermions. And I'm going to maybe put like 10 fermions, identical fermions, on the x-axis. I'm going to scatter 9 of them randomly, and then have one of them move across. And all of them are going to be sort of have an individual particle sort of Gaussian distribution, but then I've got to fully anti-symmetrize, which takes some work. I think there's a homework problem having to do with the Slater determinant, which has to do with if you have more than 2 particles, what do you do to fully anti-symmetrize? All right, so The locations of those red dots on the bottom axis are where I've placed individual identical fermions. And I'm only moving the one red dot. And notice the peaks, again, never really pass through each other. They just sort of get shoved a little bit to the side as it moves through, but you don't see one peak passing another peak in there. Sort of an interesting phenomenon that even though these things are really close, the peaks stay far apart. Let me run it again. Each time it randomizes the location of all the ones on the bottom. You might expect the peak of one to pass through the other, but they always keep sort of a generic separation from each other as they move across. So that's just illustrating the tendency of, even though you have identical fermions in almost exactly the same state, the probability densities indicate that they're likely to be found farther apart than you might otherwise suspect. Okay. Stop share. Why did I do that? I'm not sure. Okay. Okay. Let's talk about one last thing that I think is at the very end of section 5.1, which is we've been in our discussion of identical particles ignoring the spin state so far, although we did talk about combining spin states back at the end of chapter 4, and we're now going to include those things together. So, you know, if you've been paying attention, you would say, you know, we're talking about electrons, they're spin 1/2 particles. We want the entire state, which includes the spatial wave function and the spin, to be either symmetric or anti-symmetric if we have identical bosons or fermions when we exchange particles 1 and 2. That's the rule. It's not just that the spatial part has to be anti-symmetric, the full thing has to be anti-symmetric. And if the spin part of the wave function is already anti-symmetric, then the spatial part better be symmetric so that the whole thing gets a product of -1 under exchange of 1 and 2. So, phrased a different way, if the spatial wave function, which I'm here denoting by psi, is symmetric under interchanging 1 or 2, then this 2-element spinner, which I'm denoting by chi, that's Griffith's notation, has to be anti-symmetric under the interchange of particles 1 and 2. And, you know, here I'm imagining the spin 1/2 case. So these are like our 2-element spinners for spin 1/2. And so we already talked about how when we take the individual descriptions, they don't have any symmetry necessarily under the interchange of 1 and 2. But when we combine them in a certain way into a singlet state or a triplet state, we found out the singlet state was anti-symmetric under the interchange of the 2, right? The singlet state was, it looked like up, down, minus down, up, where this is the spin of Z spin of particle 1, Z spin of particle 2. This is anti-symmetric under the interchange of the 2. Whereas the triplet state, which is 3 separate states, consisted of up, up, clearly symmetric, up, down, plus down, up, clearly symmetric under the interchange of the 2 particle identities, right? And down, down. That's the spin triplet state. So what we've got to keep track of, and this is going to be important when we start thinking about filling up atoms, is that we don't always have to anti-symmetrize the spatial wave function. We need to think about the whole shebang being anti-symmetric if we're talking about electrons, right? Identical electrons. They better be anti-symmetric when we interchange the 2 particle identities. And so if we know what has to happen to the spatial wave function, we know which kind of spin symmetry we have to have, and that tells us whether we're in the singlet or the triplet state. And again, I've lost contact with my, there we go. Now, that's important for us because, you know, you might have thought, well, you know, if you have identical fermions, you can't have two in the ground state. But probably, as you know from your chemistry class or maybe modern physics, you talk about this. You can have two electrons in the ground state because as long as their spin state is, you know, if they're both in the ground state, their spatial wave function is symmetric under the interchange of the two because they're both in the same state. And that's fine as long as their spin state is anti-symmetric under the interchange of the two, which means that if they're in the same state, they've got to be in the singlet state spin-wise to make it anti-symmetric. If two electrons are in different spatial states, you know, maybe one of them's in the ground state and one of them's in the first excited state, that might be something that happens, you know, in lithium or something like that, right? You've got one electron in the ground state and one in the first, two in the ground state, one in the first excited energy state, second energy level. You could have the spatial part be anti-symmetric as long as the spin part is symmetric, or vice versa, okay? This, I think, isn't in Griffiths, but he mentions it elsewhere, but not in this chapter, I think, that this is relevant to thinking about covalent bonding that holds the hydrogen molecule together. So here I'm not talking about the hydrogen atom, but H2, where we've got two hydrogen atoms that are going to be bonded together. And the idea is, in order to hold the thing together, what's holding it together essentially is sort of an electric charge effect, right? And we want the electrons to be, if we've got the locations of the two hydrogen nuclei in a certain location, if we have the electrons highly likely to be found in the middle, then that negative charge that's sort of in the middle on average is going to be pulling those two positive charges inward and create a kind of bonding thing, right? In other words, attract the nuclei inward because the electrons are spending a lot of time at the center. How are we going to make that happen? Well, if we make the spatial part of the electron wave function, so we got two electrons involved in a hydrogen molecule. If we make the spatial part of the electron state symmetric, what that means is, according to our, you know, when we symmetrize these wave functions, you tend to get them to be more likely found in the same vicinity, which means they're going to be found in the center. You're going to have higher probability of finding them in the center. But this thing is almost not responding anymore. And that is possible as long as the spin factor is anti-symmetric in that case. So you know, you can figure out a lot about chemical bonding just by thinking about what has to hold molecules together. I may have to stand over here at the computer. My pointer is just not working. Yes, so it has to be in the anti-symmetric singlet state, the electrons in that case. Okay, let's get into now section 5.2, which is sort of a crude model of how to think about the structure of atoms. And maybe you've talked about this in your chemistry courses, but now we can think about it in light of what we've learned in quantum mechanics. We'll start out thinking about helium because it's the next most complicated case beyond hydrogen, right? We want to find the definite energy states, energy eigenstates, and the energy eigenvalues, which means we need to solve the time-independent Schrodinger equation. And the Hamiltonian in that case has three different parts. There's a kinetic energy part for electron 1, and then there's a potential energy between electron 1 and the nucleus, right? There's a kinetic energy term for electron 2, and there's a potential energy between electron 2 and the nucleus. But of course, the two electrons interact with each other. So there's also a kinetic energy, right? K, Q1, Q2 over R, potential energy associated with the two electrons. And it's positive because the two repel, right? It's a positive potential energy term there. Well, these are both electrons in this case. So that M is an ME, mass of the electron. Dare I try with my pointer? It just seems to lock up after a minute. Okay. There's some, this is sort of the most basic Hamiltonian. If you consider more dynamics, there's slightly more complicated Hamiltonians that make slight adjustment to this, but this seems to make sense as a pretty solid capturing of all the energies that are going to take place, that are going to be important for the helium atom. Okay, so we're going to describe our total state. Come on. No. Total state is a spatial wave function as a function of the positions of the two electrons. Again, we're going to consider the helium nucleus to be fixed kind of at the origin and just be a background potential energy. And then we've got the spin state of the two electrons. Okay. Now, when you separate out variables here, you can separate out the spatial part and the spin part. And in this case, the Hamiltonian doesn't depend on the spins at all. So when you separate out the spin part from the spatial part, you find that the spatial one satisfies this full time-independent Schrodinger equation that just has to do with the spatial state. And the problem with this is this last term here. Finding analytic solutions is, well, nobody knows so far how to find any analytic solutions. The only hope we have is for numerical solutions if you include this electron-electron interaction term. And so just to get an idea about it, and actually it's amazing the amount of mileage you can get out of this, we're going to ignore the interaction between the electrons. In other words, we're going to consider them to be non-interacting identical fermions, those two electrons. So they're both attracted to the helium nucleus, but we're going to pretend that they don't repel each other at all. And a lot of times people will then say, well, okay, when you get the energies, you can sort of imagine, well, then how would the electron-electron interactions change things? It might increase energies a little bit because the electrons are repelling each other, and some, depending on the shape of the orbitals, it might affect things more than others. Okay, so if we ignore that electron-electron interaction term, just throw it away and say, let's just pretend that each one of these electrons is in something very similar to a hydrogen atom, except that the nucleus is different, right? A hydrogen nucleus just has one proton. A helium nucleus has two protons, so there are two E charges at the center of it. But other than that, it's very similar to a hydrogen atom, sort of a trivial change. And in that case, it's pretty clear because this is just a sum of two terms, one that only has to do with R1 variables, one that only has to do with R2 variables. Therefore, you can further separate variables into a product wave function, a function only of R1 and a function only of R2. And those factors are individual hydrogen-like wave functions. In other words, they have quantum numbers n, l, and m, because it's almost like a hydrogen atom. The only difference is there's a little bit more charge at the origin. Right? It's double the charge of a hydrogen atom, but we can look at the energy levels and kind of figure out what to change there by just looking at the formula. So for example, here is the hydrogen atom energies right here. This m is the mass of the electron. In this case, this e to the fourth is actually going to get modified because two factors of those e's came from just the one e charge of the proton at the origin, and now we've got a 2e charge of the helium nucleus at the center, which then gives a factor of 4 difference in the energies. In other words, the helium energies get a factor of 4 up here, right? 2 of these factors of E from the E to the 4th come from the electron. That's not different, but 2 of them come from the nucleus, and those get multiplied by 2. So we get a factor of 2 squared, or 4 up there. And so we can think of the total energy for one of these states, where the 2 electrons are in these kind of hydrogen-like states, as the sum of the energies for each of the electrons, right? So we're going to say electron 1 is in a hydrogen-like state about the helium nucleus, and electron 2 is in a hydrogen-like state. And the energies are the sum of the energies of the individual ones, but they're 4 times the corresponding hydrogen energies, just because double the charge on the nucleus. If you follow through where this came from, you'll see why 2 factors of E correspond to the nucleus and 2 correspond to the electron. Okay, and therefore we can figure out what the ground state wave function is. Ground state wave function is where both electrons are in the ground state. Again, that's allowed because we can just make their spin state antisymmetric, and that's going to make the total state antisymmetric. So their spatial state is symmetric in this case if they're both in the ground state, but that's okay as long as we put them in the spin singlet state. And you get a very similar kind of wave function that's almost the same as the hydrogen wave function for individual hydrogen electrons, but this one has an R1 and an R2 in it. Yeah, so I'm just reading through this and trying to remember what I'm saying here. The ground state of helium should have an antisymmetric singlet spin configuration because the spatial wave function is symmetric, clearly, because it's a product of 2 of the same factors. The excited state, Griffiths explains why the excited states of helium, if you put both of them in an excited state, it doesn't last long at all. Of course, if you put one of them in one electron in an excited state, it will transition down to the bottom. But if you put both in an excited state, it will actually eject one of the electrons and you won't be left with helium for very long. So we're going to consider the excited states to be the ones that might transition to the ground states. They are the states where one of the electrons in the ground state and the other one is in some higher energy level and might transition back down to that ground state by emission of a photon, which of course our quantum mechanics doesn't tell us about because electrons don't interact with photons in non-relativistic quantum mechanics. Okay, and now just a reminder that because if the 2 electrons are in different spatial states, and here we're talking about one in an excited state and one in the ground state, we have 2 possibilities for how the spin part could have symmetry or anti-symmetry. The spatial state is anti-symmetric under interchange, and we can make it that way just by anti-symmetrizing this one with this one, right? This isn't going to be just by itself. This product doesn't have any symmetry under the interchange of R1 and R2, but if I symmetrize it, that would make the spatial state symmetric. And then I guess that's my second bullet down here. Then the spin part has to be antisymmetric. That would be the spin singlet state, and vice versa. I could make this antisymmetric, the spatial part, by antisymmetrizing, and that would tell me the spin part has to be symmetric. And so those are, people divide this, and there's good spectroscopic reasons for dividing these 2 different cases for the excited state into 2 different kinds of names. I'm not sure where the para and ortho comes from in this case. You can ask a chemist about that. But perihelium refers to cases where the spin state is the singlet spin state, where excited states. And orthohelium refers to where the spin state is the triplet, which is symmetric under the interchange, which means the spatial wave function is anti-symmetric. Yeah. Now, all of this is predicated on the fact that we've ignored the energies of the electron-electron interactions. And so in the case where we make the spatial wave function symmetric, that's perihelium, the electrons tend to be closer together on average because we've made it symmetric. When you symmetrize a wave function, you tend to get higher probabilities of the 2 particles being closer together. And that means that the perihelium states, the ones where the spatial wave function is symmetric, tend to have higher energies because we know we ignored that spatial wave function, but if we make the spatial, we ignored the electron-electron interaction, but if we make the spatial wave function symmetric, the electrons are going to spend more time near each other, and that means the electron-electron repulsion is going to add some energy to it. And what that means is if we look at the energies of the various excited states of helium, again, one of them is in the ground state and the other one is in an excited state. What this is showing is the energies, the combined energy, of course, the ground state one always has the same energy, but the one in the excited state determines the energy. We find that perihelium states always have slightly higher energies than the corresponding orthohelium states. But in any case, that gives a slight splitting in the energy levels that you see in excited states of helium. Okay, let's now think about building up the periodic table. Again, we're going to proceed the same way just to kind of get a very crude idea of, gosh, I keep losing track of where things are here. Sorry about that. We're going to ignore the electron-electron pieces and we're going to keep adding one more proton to the nucleus and one more electron and try to figure out in what order things build up. And then we can construct a crude kind of model of the periodic table. And the exact details, it works pretty well. And then at some point things start to fall apart because we're ignoring some energies and things start to change orders in which the orbitals fill. Okay, so the idea is we're going to imagine if we have like carbon, that's Z equals 6, that's got 6 protons and 6 electrons in a neutral atom. We're just going to pretend that all 6 of those electrons are in hydrogen-style orbits. Slightly different because there's 6 protons at the origin rather than just 1, but other than that, we're ignoring all the electron-electron interactions. And therefore, we just, in our original formula, everywhere there was an E for the nucleus, we just replace it with ZE if we're considering an atom with atomic number Z. Okay, and we'll label them the traditional way with N's, L's, and M's. Since they're fermions, only 2 can occupy each orbital. In other words, when we've got an atom that's filling up, we can have 2 electrons in the ground state. We can have 2 electrons in the next highest energy state because they're allowed to be in a symmetric state under interchange as long as we make the spin state anti-symmetric singlet configuration. And of course, there's a lot of, for each particular level, N, there's a huge degeneracy for the hydrogen atom. It has a degeneracy of N squared. Now that degeneracy isn't really there in the other atoms because the electron-electron interactions change the energy levels quite a bit depending on exactly how much it's filled in. But in this crude model, we remember that for, if you're in the 3rd energy level, the degeneracy for the spatial wave functions was 3 squared or 9. Now, if we include the spins, we're allowed to put 2 times 9 or 18 into the N equals 3 level, right? The N equals 1 level has a degeneracy of 1 spatially, so you can put 2 electrons in it. 1, because we put them in the anti-symmetric configuration, okay? So each N value, right, we're starting with hydrogen wave functions, N equals 1. We call each of these N's a shell. So N equals 1 can fit 2 electrons in it. N equals 2 can fit 8 electrons in it. N equals 3, 18 electrons, and so on. We just calculate what 2N squared is. Okay, we're ignoring a lot of electron-electron interactions, but let's just see if we can figure out the structure of the periodic table here. The idea is, roughly speaking, each row of the periodic table corresponds to, or at least when you get up to the right-hand side, you've filled up a particular shell. So once I've, here's a 1 electron atom, here's a 2 electron atom. That's when I filled up the N equals 1 case, right? I've got 1 spin up, hydrogenic atom electron, and one, well, not one spin up and one spin down, but a spin up, spin down in an antisymmetric state. So I filled the level n equals 1. When we get to neon, we filled n equals 2. When we get to argon, we filled n equals 3. But the details are a little bit more complicated. I mean, it sort of goes that way, at least at the beginning, but then we're going to have to adjust things because our model is ignoring those electron-electron interactions. Okay, so with helium, n equals 2 is filled. That's all we can. I'm sorry, I'm not sure why it says n equals 2 is filled. N equals 1 is filled for helium. That's a typo there. And then for lithium, that's Z equals 3. It's going to go in the L equals 0 state. Now, for the lithium, we're talking about, okay, we've already filled up n equals 1 with 2 electrons in that state. Now we've got a third electron. It's going to have to go in n equals 2. For n equals 2, we have two choices for L. L equals 0 or L equals 1, right? It goes from 0 up to n minus 1. And the argument here is that, well, it's going to go in the L equals 0 state before it goes in the L equals 1 state. And it's going to go in the L equals 1 state before it goes in the L equals 2 state for the following sort of, slightly sketchy argument. The inner electrons screen the nuclear charge. So I'm not sure I quite exactly understand what I'm saying here. Makes sense, which means that the electrons spend time farther from the nucleus, and the inner electrons screen the nuclear charge. So the electrons that we've already used to fill up down those lower levels, if we're considering placing in an electron, screen the nuclear charge. And if you're spending more time farther away from the nucleus, they're more completely screened because those other inner electrons are more completely at radii smaller than you, and therefore they're not as strongly held. Remember, strongly held electrons have negative energy. Higher energies correspond to more weakly held electrons. Okay, so the L equals 1 energies, just by this sort of very, hand-wavy argument, should be a slightly higher energies than L equals 0. So when we're filling up the n equals 2 row there, we're going to fill up the L equals 0 state first, and then the L equals 1 state. Okay, so lithium, we get 1 electron in the L equals 0 state, and then for beryllium, we get 1 electron, the second one in the L equals 0 state, and then we start filling up the L equals 1 states. M sub L can go between -1 to 0 to 1, and there's 2 electrons per each one of those because we can anti-symmetrize the spin states, and so we get 6 L equals 1 states. So for L equals 0, there's always 2 electron states. For L equals 1, there's always 6 states, and so on. You can figure out for L equals 2 what the number would be. Unfortunately, once you get to the third row, things become more complicated because we're ignoring those electron-electron interactions, and so our energies aren't quite right here. The hand-waving argument, again, is due to thinking about screening effects. So it turns out that before you fill up the n equals 3 row, you jump down and fill up n equals 4 row. In other words, I don't quite get to fill up this row until I've started into the n equals 4 row, and that's because of some screening effects where the inner electrons partially shield the nuclear charge. In our model, where we're ignoring electron-electron interactions, we don't know anything about that because electrons affecting other electrons is what screening is all about. So the idea is in n equals 3 level, we only put in, there's a lot more than 8 electrons that fit in the n equals 3 level because we should include the L equals 2, but we only fill up the L equals 0 and L equals 1 level. And then we jump to the n equals 4 state and start filling it up with the first couple of electrons. So we fill up, this is n equals 4, L equals 0, these two states. And then these correspond to n equals 3, L equals 2 states, shown there in purple. And then we're back to the n equals 4 states and filling up the n equals 4 ones. So things get a little bit out of order because it's not too surprising because we're ignoring a lot of effects. Here's someone's, so here I'm just taking a random example from the internet. Zirconium, Z equals 40. We got 40 electrons in there, 40 protons in the nucleus, right? And we're sort of roughly going to think of them as all being in hydrogenic kinds of wave functions, stacking up from the bottom as best they can. What is shown here is sort of the relative locations of the energy levels, increasing energy going up, but it's certainly not to scale. I mean, these are not spaced appropriately here. They're just supposed to be shown where they fall vertically relative to each other. So the 4D, well, I guess I've got to talk about what D and P means. You've learned about this probably in chemistry or modern physics. That spectroscopic notation just corresponds to the L states. L equals 0 corresponds to S, L equals 1 corresponds to P, L equals 2 corresponds to D, and L equals 3 corresponds to F. It's a pain to remember all this stuff, but I guess if you're a chemist, you deal in that notation all the time. So things feel sort of out of order. Oops. Come on. Still lost control of my pointer. I really want to point here. Let's see if I can get it back. Yes. So things fill out of order. Of course, we first put the 2 in the very equals 0. Then we fill up n equals 2, L equals 0, 2 states, antisymmetric singlet configuration. Then we fill up the 2p states. That corresponds to L equals 1 and M sub L equals -1, 0, or 1, 2 electrons per each. Then we start filling up the 3s state and the 3p states, but before we get to the 3d states, those are the L equals 2 states, we then start in filling up level 4 and then jump back to level 3. And so all of this is you're just going up and filling in these levels one at a time, energy by energy, until you get up to Z equals 40, which partially fills the 4D states. That's L equals 2 for n equals 4. All right, some people get really excited about this. I know physicists tend to glaze over when you start talking about chemistry stuff. Okay, as I said, the atomic state notation, which is pretty much universally used, even in physics, people use this notation. S means L equals 0, P means L equals 1, D means L equals 2, and F means L equals 3. So for example, if we wanted to say where the electrons were in carbon, carbon Z equals 6, so there are 6 electrons. The spectroscopic notation says 1s, the 1 down here in the parentheses means n equals 1, S means L equals 1. You just got to remember that, and there are 2 electrons filling up that. N equals 2, L equals 0, 2 electrons in that state. N equals 2, L equals 1, that's what P state means, and there are 2 electrons in there. So we've only partially filled the L equals 1 state for N equals 2, just because we ran out of electrons in carbon. But if you keep sticking them in, you would get this filling up to, sort of, it's not really supposed to be a power, but a superscript of 6. It would go up to 6, right? That could fit in the L equals 1 state there before we jump up to N equals 3. Okay. Yeah, my memory is it's complicated, and sometimes things even, let's see, if we go back here, things can get out of order in a weird way. Like my memory is, even for the case that's shown here, we're showing the 5s filled up. So that's N equals 5, L equals 0. It's like you put one in, they put you the other in. I think as you add another electron or 2 in here, one of the electrons maybe won't go in that 5s, because as you add more electrons, actually all these energy levels shift a little bit. because the electron-electron interactions are making them shift. If we ignore the electron-electron interactions, then so it may be that I'm showing 2 electrons in the 4D. There could be up to 10 in there, right? That would fit in there. As you go up a couple, it may be that as you're putting this, you put in an extra electron there, one of these disappears from the 5s and appears up there in the L equals 2 state. And then you add another electron and it jumps back to, it just depends exactly where the energy levels are. So they don't fill, especially as you get to high Z values, they don't fill in any nice, neat order.
Yeah, but like if we're talking about boron, where it has just 1 electron, the L equals 1, I guess. Yeah.
Yes.
Like, could that 1 L electron be any of the M sub L values? Like, do boron atoms have?
I don't know. You're asking whether the M sub L value go.
Yeah, like, do all boron atoms have their highest
I don't know. I would defer to a chemist on that. I mean, I'm really kind of naive about all the, chemists, of course, have all these sort of qualitative rules that have been developed semi-empirically to sort of match all the measurements that have been made. And I don't really know, someone could probably make a screening argument, and I'm, of course, bigger L means bigger total angular momentum. M sub L just corresponds to an orientation, so it doesn't necessarily affect how far out those electrons are going to be. So my answer is I don't know. Yep.
I feel like for the probability density we just had, there was like a 4 state, but there is no like L equals 3 state.
I'm sorry, was it a few slides back? Is that what?
It was like in the previous, like in chapter 4, we had all the probability densities. It was like 4, 0, 0, 4, 4, 1, 0. Like I thought there was
You're saying for NLM?
Yes.
4, 3, 3?
Yeah.
Yeah?
But in the last slide, it only showed like 2 sides. I don't know what that.
So do I have to keep going back, or? I don't think it's this far back, right?
There was a slide where it said like what the S represented for the L's, what the D represented.
Oh, okay. Yeah. Somewhere up here. Sorry about that. There, this one. Yeah.
Okay, so that's not.
Yes. I mean, so you remember the general thing is that N can be 1, 2, 3, and so on going up for hydrogenic wave functions. L can be from 0 up to N minus 1, and then M should be able to go from minus L up to L in integer steps. So whatever L is, you should be able to have that M associated with it. So there's still, are we okay there? No, no. It's just that beyond that, you're starting to get to kind of really esoteric elements that you don't run into in chemistry. So maybe someone can tell me from their chemistry knowledge what letter comes after F. I don't even know, because people always say
G,
S,
I
P,
think.
D, F. Sorry, was that you, Elvis?
Yes, I'm not certain how valid it is, but I was told in modern physics too that G came after F, and then H, and then I, etc.
Gracie, do you have any idea?
No, honestly.
Yeah, I mean, you're getting most of chemistry just by doing SPDF. So, but okay, GH. Okay. Yeah. Yeah. Or unstable elements. I can't remember. I think I scanned this from Griffiths, so this may be a table in there, but just showing in the spectroscopic notation what the electrons are as a function of Z, for as we're increasing by 1 electron each element here. And typically, because people, once you fill a shell, all the atoms above there will have those same filled shells at the bottom. So once you've passed one of these noble gases over here, once you pass neon, people just tend to say, oh, well, everything in neon, and then here's what's left in the unfilled shells above there. But you'll see as we go down here, things start getting out of order, right? We started filling 4, but then we go back and we still filling up some of 3 down there and so on. Okay. Do we have enough time for this? No, we don't. We're out of time. Maybe we can do this worksheet on Monday. And that's it. That's all I have to say on section 5. So I would say read 5.2. If you got questions on it, we can talk about it on Monday. We can do a worksheet associated with it and bring any other questions you have for the whole course. It might be a good time to, if you have a chance, look at those problems that I handed out in class of the grab bag of stuff that we were working on yesterday at the end of the class. And if you have any questions on those, we can talk about them too. Did I post the solutions to those? I don't think I did yet, but I will. And that's it. That's all she wrote. If you want, go ahead and read about periodic potentials. In other words, the beginnings of condensed matter physics is section 5.3, but traditionally I haven't covered that in this course.